Hi guys, so we'll be looking at magnetic properties of transition metal complexes. So there's three different magnetic characteristics. There's diamagnetic, paramagnetic and ferromagnetic, and you should be able to identify if a certain metal, a transition metal complex has any specific magnetic property. So for you to identify diamagnetic or paramagnetic, you have to look at the electronic configuration. If there is no unpaired electrons, means that it is diamagnetic. Let's take, for example, Cu plus, so with oxidation state +1. So copper has electronic configuration Ar4s1 3d10. So Cu plus is going to lose one electron. So this electron is going to be lost. This is going to be empty. So you're left with a completely filled d orbital. Now, this means that there is no unpaired electron here. All the electrons are paired. Hence, it is diamagnetic. But if you look at Mn3+, so Mn has electronic configuration Ar4s2 3d5. So Mn3+ is going to lose 3 electrons. So then you'll have only 4 electrons in the 3d orbital. So this is going to be empty, and then 4 electrons, 1, 2, 3, 4. So as you can see here, you have only unpaired electron. If there is unpaired electrons, it's going to be paramagnetic, right? So diamagnetic, no unpaired electrons. Paramagnetic, there is just unpaired electrons. But when you look at ferromagnetic, for you to remember ferromagnetic metals, you have to know the metal. So it's iron, cobalt, and nickel. You have to remember these three. These are the typical magnetic materials that you are familiar with. So let's see the configuration of nickel 2+. So nickel is actually Ar4s2 3d8. So nickel 2+ is going to be losing these 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So here you have a mixture of paired and unpaired electrons. So this is why I'm telling you that for ferromagnetic elements, you need to remember which one they are. So iron, cobalt, and nickel. So let's see about ligands. So what are ligands? A ligand is a neutral molecule or an ion that has at least one lone pair of electron that can be donated to a central metal ion. So that's the definition that you need to know. But let's see what they are. So these are examples of ligands, and as you can see, so here these are neutral molecules and these are charged molecules. So here you have water, ammonia, carbonyl, chloride, hydroxide, cyanide. So these are ligands, and what you will see that in all of them, these are lone pair. This is a lone pair of electron. It's an electron pair that is not used in any bonding. So it is available to be donated to a metal ion. So here you see at least one of the lone pair should be available. Like, these are not going to use all the lone pairs to form bonds. Just one lone pair is going to be used to form a bond. So, for example, you could have Fe that forms a coordinate bond. A coordinate bond is a very special type of covalent bond where only one of the atom provides both electrons. Usually, you know that if you have, let's say, you have a covalent bond between H and O, you know that H will contribute one electron and O will contribute another electron. But when you have a dative bond or a coordinate bond, one of the elements of the atom will provide both electrons. So let's say oxygen is providing both electrons to hydrogen, let's say, yeah? So this is what is going to happen over here. So here, if Fe2+, let's say it's forming a coordinate bond with CO, the carbon is going to provide both electrons. So we could show it like this. The arrow shows that carbon is providing both electrons to iron. And similarly, you could have 5 CO molecules, so 5 carbonyl molecules that are forming coordinate bonds with Fe. And Fe is going to maintain its overall charge as 2+. So this is a complex compound, and so that formula would be 5 2+, like that. So this is a complex compound, and the CO, the carbonyl, is acting as a ligand. So here this is called pentacarbonyl ferrate or pentacarbonyl iron 2. So this is showing the oxidation state of iron. So these are all ligands that can form complex compounds. And if you read here, it says the transition metal ions are small and highly charged. Because they're small and highly charged, they are able to attract these ligands which have high electron density. So this lone pair is providing electron density, so it's attracting it, forming a complex ion in which coordinate or dative bonds links the metal ion to the ligand molecule or ion. So this is a coordinate bond that you see here. Okay, so make sure you know this definition. Now, ligands or ions or small polar molecules, I hope you remember when I explained about polar molecules, saying that because there is a difference in electronegativity, so let's see here, oxygen is more electronegative than hydrogen, therefore it pulls electrons towards itself. It will be delta minus, and hydrogen is going to be delta plus. Because this is delta minus, a partial negative charge, it is a polar molecule, so this is going to be attracted by the Fe2 plus. This is what drives the oxygen to become close to the Fe2 plus, and then the lone pair of electron is donated to the Fe. Alright, so this is what happens. Let's see different kind of ligands. We have monodentate ligand, bidentate ligand, and polydentate ligand. So a monodentate ligand is one that is going to donate only one pair of electron. So the ligand can have 2 or more electron pairs, but only one electron pair will be donated. So for example, like H2O, there it has 2 lone pairs, but only one is going to be donated to the metal ion at one time. So here you could have the Cl minus forming a dative bond with, let's say, Fe2 plus. So this is donation of one electron pair. Now a bidentate ligand is going to donate 2 electron pairs at the same time. So what happens, so this is how it's going to bond with the metal. So this is the metal, and this is 1,2-ethane diamine, and each nitrogen is providing one lone pair of electron, and these 2 lone pairs, so this molecule is able to form 2 dative bonds at once, and it kind of holds the metal like a claw, and therefore is called as a chelating agent. All these are chelating agents. Bidentate ligands are chelating agents, and all of them are going to hold the metal like a claw. Right. Now polydentate ligands, one very famous polydentate ligand is EDTA, and here EDTA can form, it's a hexadentate ligand, it can form 6 dative bonds at once, and this is how it holds the metal. So you can see here that the metal is at the center, and everything here, that's one molecule. That's only one molecule over here. And in that one single molecule, there is 1, 2, 3, 4, 5, 6 lone pair of electrons that are donated. So you can see that the metal is like a prisoner in the EDTA ligand. Now, naming of complexes, actually you don't really need to know how to name complexes. It's just for you to have an idea of how they are named. But you need to know the charges on the ligands. It's very important for you to know the charges and to know which are the neutral ligands. So this is how you name the ligands. Okay, so there is 6 water, so hexa, aqua, copper 2. There is 6 cyanide ions, so hexacyano iron, and this is the oxidation state of the iron, and this is the oxidation state of the copper. So you can use the list to find the names of the ligands. Now let's see, you need to find the oxidation state of the metal. So if you have this complex compound, so let's say the oxidation state of copper is X. There is 4 Cl, so 4 times the oxidation state of Cl. So Cl is -1, so it is, it's not in the list, so you could add it. Cl is chloro. Okay, so Cl minus, charge is -1, and when you add everything, it should give you the overall charge of the complex, so 2 minus. So X minus 4 gives you, well, actually -2, therefore X would be 4 minus 2, that gives you 2, which means that you have copper in the 2+ oxidation state. Okay. Now, if you look at Fe, so this is the hexa-aqua complex of iron. So, because this is a neutral ligand, it does not contribute to any charge. So, iron is X. So, X is equal to 3+. So, then it's Fe 3+. So, you could name that hexa-aqua iron 3+. Here you go. Here you have 6 Cn, so Fe is X plus 6 times -1 is equal to -4. So X minus 6 is -4. Therefore, the charge would be 6 minus 4, so +2. So then it's Fe 2+. So this is how you can find the oxidation state of the metal. Let's try this one. Here the overall charge is different, so the oxidation state of iron would be different. 6 times -1, -3, so X would be +3. So here it is Fe 3+. So that would be hexacyano iron 3. Here this would be hexacyano iron 2. Right. Let's see coordination number. So the coordination number, so the number of ligands surrounding the central ion is called the coordination number. Typically 2 to 6 ligands may surround a transition metal ion, and most common complexes involve 4 to 6 ligands. So coordination number, so you could have different number of ligands around that metal. So here you can see coordination number is 2 ligands to that metal. Here coordination number is 3. Here coordination number is 4. Here coordination number is 5. And you have coordination number 6. Now here, this is in no way related to the shape. We haven't done shape yet. So we're just looking at coordination number. How many ligands are linked to that? Now if you have like the polydentate ligand, EDTA, here the coordination number of one EDTA molecule is 6 already. Okay, so that would be it. You're going to ignore these questions because they're talking about shapes. You're going to do the end of unit question, and this marks the end of unit 13.2. So thank you and bye-bye.